Let's consider part 3 of Basics of Asymptotic Analysis. From the last lecture, we have learned that examining the exact running time is not the best solution to calculate the time complexity. That's what we have learned from the last lecture, right? It is not a best practice to know the exact running time of an algorithm. So what is the best solution to this problem? There are certain points we need to note here. Measuring the actual running time is not at all practical. We have learned this already, that measuring the actual running time is not at all practical. The running time generally depends on the size of the input. I want you to note this point, that running time generally depends on the size of the input. Now why I'm saying this? Let's see this with the help of an example. Suppose we have an array which consists of 3 elements like this. Now what I want to do, I want to add one more element to the beginning of the list. Let's say this is the element I want to add at the beginning of the list. For this purpose, obviously, I must have an empty slot here and I need to make 3 shifts. Let us assume that if one shift takes 1 unit of time, then 3 shifts will take 3 units of time. Isn't that so? If one shift take 1 units of time, then 3 shifts will take 3 units of time. I need to shift each element towards right in order to make an empty slot here. Now you can understand that with the size equal to 3, the time will also be 3 units. After shifting, this will become empty and then I can add the element in the beginning of the list. There is no problem in adding this element, right? But what if we have 10,000 elements in an array? Isn't that going to be very tedious? Because shifting is costly, right? Adding the element to the beginning of the list is not costly. Shifting is costly. In that case, we have to make 10,000 shifts, which will take 10,000 units of time, because we have assumed that one shift will take 1 unit of time. We have to make 10,000 shifts. Therefore, it will take 10,000 units of time. So it is clear from this fact that running time generally depends on the size of the input. Here in this case, it depends on the size of the array. Size of the input or size of the array, one and the same thing. So if the size of the array is 3, it takes 3 units of time. If the size of the array is 10,000, it will take 10,000 units of time. The one thing we should note here is that it totally depends on the size of the input, that what is going to be the running time. Obviously, we are not considering the machine time, that how much time a particular operation will take in a particular machine. We are considering only the size of the input. So running time generally depends on the size of the input. This fact we should always remember. Therefore, if the size of the input is n, then fn is a function of n denotes the time complexity. So fn is nothing but a function which denotes the time complexity. It depends on input n. Okay? Or in other words, I can say fn represents the number of instructions executed for the input value n. Let's consider an example to understand this statement. Here in this example, I have a printf function within this loop which runs from 0 to n minus 1. Let's say this instruction will take 1 unit of time. This is my assumption. Let's say this particular instruction takes 1 unit of time. Then we are executing this instruction n number of times. So this is clear that fn will be equal to n. Because each instruction is taking 1 unit of time. And we are executing this instruction n number of times. Right? We are executing this instruction n number of times. That is why it depends on the size of the input n, and fn will be equal to n, because fn is keeping the count of the number of instructions executed for the input value n. This will give us the time complexity. But how to find fn? Finding fn in small programs is easy, but as programs become more complex, finding fn is not that easy. We can compare two data structures for a particular operation by comparing their fn values. We can compare their fn values and then we can compare two data structures. We are interested in growth rate of fn. This is very important. We are interested in growth rate of fn with respect to n. Because it might be possible that for smaller input size, one data structure may seem better than the other, but for larger input size, it may not. This is very important. We are interested in growth rate of fn. We have to try different values of n and then we have to find what is going to be the fn value. So for different values of n, we should calculate, not for just one value of n. Because it might be possible that one data structure may seem better for smaller input size than the other data structure. This concept is applicable in comparing the two algorithms as well. It is like, we can compare two algorithms in the same way. We can compare two data structures in the same way. We are interested in growth rate of fn. Now, how to know the growth rate of fn? Let's consider one example. Let's say we have fn equal to 5n square plus 6n plus 12. This represents time or number of instructions executed. That depends on the input value n, of course. Let's say initially we take n equal to 1. then percentage of running time due to 5n square will be 5 divided by 5 plus 6 plus 12. We just have to put 1 here. This becomes 5. This becomes 6. This is already 12. So 5 plus 6 plus 12. We will divide 5 by 5 plus 6 plus 12 and then we will multiply it by 100 in order to calculate the percentage. This will give us 21.74%. So we can clearly say that percentage of running time due to 5n square is 21.74%. 5n square is contributing this much amount of time. Obviously this we are calculating for n equal to 1. Let's see what is the percentage of running time due to 6n. It is 6 divided by 5 plus 6 plus 12 into 100, which is 26.09%. So 6n is contributing higher than 5n square, right? Now let's see what is the percentage of running time due to 12. It is 12 divided by 5 plus 6 plus 12 into 100, which is 52.17%. It seems like most of the time is consumed here. But wait, we have to see the growth rate. We cannot say right now that maximum amount of time is taken by this 12. Let's see for the other input values as well. Let's say n is equal to 10. In that case, 5n square is contributing 87.41% of the running time. You can clearly see the growth here from 21.74% to 87.41%, while 6n is decreasing. It decreases from 26.09% to 10.49%. And 12, which we thought of as taking most of the time, is now taking just 2.09%. Now let's take n value equal to 100. In that case, you can clearly see the growth. 5n square is contributing the maximum of the time. It is 98.79%, while this is just taking 1.19% and 12 is just taking 0.02%. If you increase the n value further, you can clearly see 5n square is taking 99.88% of the time, while 6n is taking 0.12% of the time and 12 is just taking 0.0002% of the time. These are almost negligible, right? Most of the time is consumed here, that is in 5n square. 99.88% of the time is consumed. So from this fact, it is clear that for larger values of n, the squared term consumes almost 99% of the time. This term is consuming the most of the time. Let's say you have taken the value of n equal to 1 and you simply say that 12 is taking the most of the time. But the reality is different. As you are increasing the value of n, you can clearly see which term is taking the most of the time. Now let's visualize the growth rate. Here you can clearly see that squared term is taking most of the time. The growth you can see clearly over here. While the growth of the constant term you can also see. Initially it is high, but later it declines faster. Similar for the linear term as well. You can clearly say that this squared term or quadratic term is taking the most of the time, right? So there is no harm if we can eliminate the rest of the terms as they are not contributing much to the time. We can eliminate these terms, 6n plus 12, we can eliminate them. There is no problem in eliminating them because we know that 5n square term is taking the most of the time. It is 99.88%. We are getting the approximate time complexity, isn't that so? And we are satisfied with this result because this approximate result is very near to the actual result. If we take fn is equal to 5n square, there is no harm. We know that it is taking 99.88% of the time, or it may take even more. We are getting the approximate time complexity and we are happy with it. There is no problem in eliminating the rest of the terms. This concept of calculating the approximate measure of time complexity is called asymptotic complexity. We are not calculating the exact running time here. We are eliminating the unnecessary terms. We are only concentrating on the term which takes most of the time. Okay? So this approximate measure of time complexity is called asymptotic complexity. And this is what we are interested in. We are not interested in calculating the exact running time. We are not interested in which machine we are executing our algorithm. We are only interested in calculating the approximate measure of time complexity. And we are satisfied with this result. We already know this fact that time complexity depends on the size of the input. As you increase the size, you can see the time complexity changes. So it depends on the size of the input and we are happy with this result. Okay friends, this is it for now. Thank you for watching this presentation.